Today, I will present my solution for assessment 1 which focus on designing an FIR low-pass filter for a battery-powered portable biomedical device. For part 1, based on the given specification, I have sketched the ideal and actual magnitude response. The pass band edge frequency, omega p, is calculated at 0.4 pi radian per sample, and the stop band edge frequency, omega s, is at 0.6 pi radian per sample. This gives us a transition y beta omega of 0.2 pi and an average cut-off frequency omega c right in the middle at 0.5 pi. Moving on to part 2, we need to manually design the filter coefficient using the Henning window method. By using the transition weight formula, we found that the required window length n is 31. Since n is an odd number, our center of symmetry alpha is exactly at 15. To find the actual filter coefficient Hn, we multiply the ideal impulse response Hdn with the Henning window function omega n. Here are the sample calculations starting from the center of symmetry. Finally, for part 3, we analyze the impact of changing the filter order from N32 to N34 on a portable biomedical device. For a filter order of 32, the filter length n is 33. This requires 33 multiplication and 32 addition, totaling 65 computational operations per sample. When we increase the filter order to 34, the filter length becomes 35. This increases the load to 35 multiplication and 34 addition, totaling 69 computational operations per sample. In conclusion, moving to order 34 forced the processor to perform an additional 4 operations per sample. For a battery-powered wearable medical device, this higher computational cost demand more clock cycles, which directly lead to higher power consumption and will shorten the overall battery lifespan of the device. Therefore, a lower order like 32 is more cost efficient for long-term energy consumption.
To answer the question of Roman, because we are designing an IIR filter using the linear transformation method, we must perform frequency pre-mapping to convert our digital domain frequency into the analog domain. The fundamental mapping formula used is omega equal tangent of omega over 2. Applying this formula to our specific passband boundary, we get omega p equal tangent of 0.3 pi over 2. This evaluates to 0.5095. Next, applying the same pre-mapping formula to our stop band boundaries, we get omega s equal tangent of 0.30.5 pi over 2. This evaluates exactly 1 over 0. Now that we have a frequency, we can calculate the performance metric for the filter. First, we determine the selective factor, which is k equal to omega p over omega s, which is 0.5095, 1.0, giving a 0.5095. Second, we calculate the discrimination factor d using our Ripple parameter. D equal to the square root of the quantity 10 to the power of Rp over the 10 minus 1 divided by 10 to the power of A s over the 10 minus 1. Substitute to our given test value Rp 270 dB and AS equal to 40 dB into the expression. We plug in 27 and 40, giving us a square root of 10 the power of 27 over the 10 minus 1 over 10 to the power of 40 over 10 minus 1. This calculation simplified to a final discrimination factor of 0.2237. Finally, use our value for D and K. We evaluate the minimum required filter order. N is greater than equal to log E based on 1 over D divided by log base E over 1 over K. Substitute our compute number into the natural log formula. n is greater than or equal to log base e of 1 over 0.2237 divided by log base e of 1 over 0.5095. This is an exact of value of n greater than or equal to 2.9314 since a physical factor must be an integer number of stages we round up to the next whole number. Our hand calculation confirms that third order butterworth factor is required. Now let's move on to part 2 Round 1 of the assessment where we need to determine the 3 dB cut-off frequency as omega c. In filter, omega c must be selected with a mathematical secondary that satisfies both of pass variable and stop band attenuation requirement. The governing formula of this range is the lower band is an analog passback frequency divided by 10 to the power of 0.1 Rp minus 1, all to the power of 1 over 2, and the upper band is analog stopgap frequency divided by 10 to the power of 0.1 as minus 1, or the power of 1 to n. By substitute our calculate factor, the n equal to t pre-warp frequency and attenuation parameter into the formula. For the lower limit, we calculate omega c 1 equals 0.5095 divided by 10 to the power of 2.7 minus 1, whereas to the power of 1 over 6, which gives us 0.1812. For the upper limit, we calculate omega c2 equal 1.c divided by 10 to the power of 4 minus 1 raised to the power of the 1 over 6, which gives us 0.2154. This gives us a valid range of 0.1812 less than or equal to omega c less than or equal 0.2154. To make our net system function derivation cleaner and easier to calculate, I have selected a clean midpoint value within this range, which is omega c equal to 0.2. Now we move to the final analytical part of our assessment part 3, where we determine the system function as based on the calculate left-hand side pool. To ensure the system is stable, we locate the pool of the butterworth filter on the left side of the S-band. Formula used to calculate this individual pole position is Sk equal negative omega c times sine of the quantity 2k plus 1 times pi all over 2m plus j omega c times cosine of the same quantity. Using our design parameter where omega c is equal 0.2 and n is 3, we calculate the pool for k equals 0, 1 and 2. Following the step shown in my calculation sheet, we solve for each pool. First, for k is equal to 0, S0 equal negative 0.2 sine of pi over c plus j 0.2 cosine of pi over 6. This gives a complex pool at minus 0.1 plus j 0.1732. Now, for k equal to 1, since 1 equal negative 0.2 sine of 3 pi over 6, which is pi over 2 plus j 0.2 cosine of the 3 pi over 6. This result is a purely real pool at minus 0.2. Finally, for k equal to 2, this is a complex conjugate of our first pool and expected for a real value system. The final step is to construct the system function Hs by taking the product of the piece-pool factor. The general form is h of s equal the product from k equals 0 to 2 of negative sk over the quantity s minus sk. Substitute our calculate pool into this expression, we got h of s equal to 0.008 divided by the product of plus 0.1 minus j 0.1732 times plus 0.2 times s plus 0.1 plus j 0.1732. When we multiply these factors together, we arrive at our final analog system function, which simplify to 0.008 over s cubed plus 0.4 s squared plus 0.08 s plus 0.008. This complete the mathematical synthesis of our butterworth filter. Is it now ready for digital transformation and MATLAB validation? To finalize and validate our analytical design, we implement the filter specification into MATLAB to cross-check our manual calculation. In our MATLAB code, we first define our digital boundary frequency WP equals 0.3 pi and WS equals 0.5 pi when then key in our attenuation variable ensuring RP is correctly set to 27 decibel and AS to 40 decibel. Next, we pass the test parameter into the Boolean button function to automatically compute the required filter order n and the normalized 3 dB cut-off frequency WN. Finally, we use butter to generate our filter coefficient and call FV2 to visualize the full magnetic response. When we execute this script with the correct parameter, MATLAB return two vector output in the comma window and then instantly validate our hand calculation. As shown in the command window output, MATLAB verified that the minimum filter order n is exactly 3. This provides perfect one-to-one confirmation with our analog calculation in part 1. Furthermore, MATLAB established the normalized digital 3 dB cut-off frequency WN at approximately 0.214 pi. If we do normalize this back to the analog domain using our pre-warping relationship, it falls precisely within the same engineering range of 0.1808 to 0.2154 that we established in part 2. Looking the final plot generated by FV2, we can visually confirm that our design track third order vector meet various single engineering constraints perfectly. In the passband region from DC up to the our cutoff edge of 0.3 pi, the magnetic response stays tightly constrained, ensuring the passband ripple does not exceed the 27 dB limit. In the stop region, as the frequency swept past 0.5 pi, the magnetic curve drops safely below the minus 40 dB line, guarantee that any high frequency power line noise is completely blocked and eliminated. This successful MATLAB simulation officially proved that our analytical derivation of HS and the subsequent IIR structure are completely accurate, reliable, and ready for the development in the power quality monitoring system. That concludes my full presentation for assessment 2. Thank you.